Okay, now we'll use a textbook example to illustrate the idea of domain estimation. Suppose that we have a list of boat owners of size 400K and a simple sample of size 1,100, owners are selected using simple sampling from this population, from this list. And the population has two domains, and the first domain is large boat, and second domain is not the others. Okay, so turns out that from the sample, this information was not available from the list. So we just use simple random sampling to obtain their status, and found that N1 472 sample owners has large boat, while 1028 owners do not have this kind of boat. From this survey, we can estimate the domain mean parameters or domain total parameters. For the domain mean, for example, we can estimate the average number of the children for boat owners from domain 1. So domain 1 means this large boat, right? So for this particular owners, we might be interested in estimating the average number of children. Or the other parameter is that can be proportion of boat owners from domain 1 who have children. Another type of the parameter is the total, and the total can be, for example, total number of children for boat owner, for large boat owner, domain 1. Or the other parameter could be total number of boat owners. So the first one is total number of children, and now second one is total number of boat owners from domain 1 who have at least one child, something like that. Okay. So let's consider estimation of domain means. For a given domain D, domain population mean is written something like this, right? So it's just a sample mean. The population mean of y in the particular domain, particular population. So this particular population is UD. Okay. So you can. The basic idea is that for this kind of estimation, the basic idea is we can express this domain mean as a ratio. So ratio of two population means. So how can we make these two equal? Okay, so that is the question. So basically, how do you define ui xi such that this population mean can be written as a ratio? Okay, here's our idea. So if you define ui, so ui is just another population characteristic, and ui equal to yi if the owner I belongs to the domain, otherwise just 0, and xi is 1 or 0 dependent on this status. In that case, summation of I equal to 1 to n is what? Is of xi is what? Equal to summation ud, right? So that means just we just count the count. So I is just the indicator. So if that is true, then it's 1, otherwise 0. So basically this one becomes ND. So this one is ND. And numerator, summation of UI is what? So that is actually equal to UD yi. So that means I equal to ud yi. So that basically we have this equality. Okay. So that so basically we just show that this original domain mean can be written as a ratio of two population means. So now that we have written as a domain mean as a ratio of the two population means, we can apply the estimation formula for the ratio. So basically, this is the parameter itself is a ratio of two population means, and so the estimator is just the corresponding sample, the ratio of the sample means. And sample mean, so this is estimator of u by u, and this is a unbiased estimator of x by u, right? So just as basically we just use a sample mean to estimate the population mean for each domain. And now, what is this? So what is this? So that means this guy is what? Right? Because of the definition. So that means okay, what should I write it? Well, okay, basically you could write it so you can, so it should be we are counting, okay, we are counting the number of elements in the union. So we are basically computing the union of intersection of this. So that is SD. Okay. Same way, what's this? That is I equal S yi times I equal to ud. So that becomes yi. Okay, so that's this one. So using these two, we basically obtain p hat equal to the sample mean of y among the elements in SD. Okay. Now let's discuss variance and variance estimation. So recall that so the catch is that let's make use of the formula for ratio estimator. So this is the ratio estimator of y bar, right? So y by u. So we know the formula. We know the formula already using, that's week 10, right? So we already know this. And so, by the way, this is the because it's so becomes a y, and so we can ui and xi only defined among ti's. I mean ud. So that's why we can write it this way. So now what we are interested is actually variance of the p hat. So p hat is the ratio estimator divided by population mean of x, right? This is a constant, fixed constant. So the variance, so this one is y bar r divided by x bar u but this x bar is fixed, so this can go outside and obtain summation. So that is that's why this is variance of the ratio estimator, and we just divide it by x bar u square. Okay. So we now use the same idea to develop variance estimation. So here's the formula for variance estimation. So variance estimation of y bar r x bar u p hat. Okay, so that is the ratio estimator. So we know this formula already. So that means for variance estimation, then variance estimation of y bar r divided by x bar u. So that means variance 1 over x bar u square and variance estimator x bar r. So we can use this formula to here. Okay, and then x bar u is unknown, so we divide by we replace it by x bar instead of x bar u. So that is the formula. Okay, so turns out that this formula can be simplified to something like this. So one nice interpretation of this formula is that we can almost treat the domain mean as a sample mean, as simple mean of size nd. So you can write it as a, so here it says sample mean of y bar d, right? So among, as if the sample size is nd. So that means this is original as s, but you have a sd, right? And the sd sample size is nd. So you can treat it. So from here you obtain p hat, and now the point is, the message is that y bar d. The message is that you can basically treat it as a sample size nd, and this is just the variance. So population of size nd, and we'll prove this approximation in the next class.